today, we have a few administrative announcements. First thing is regarding your midterm 1, we finished transferring your grade from Gradescope to BrainLearn. So basically your Gradescope score will cap at 150, but your BrainLearn score will cap at 200. So based on the survey, we calculated your percentage grade and make it a 200 point exam. So check to make sure your percentage grade is the same on Gradescope and on BrainLearn. If you notice anything different, just let us know as soon as possible. That's the first thing. The second thing is for the coming week, I won't be here for Monday and Tuesday. I'll see you on Wednesday, but Monday and Tuesday I won't be here. So that means for the Monday lecture, I will upload a YouTube recording of basically me doing whatever we want to cover. And Qingyang will be here on Monday with you for Q&A and also like review things we covered before. On Tuesday, I have to cancel my office hour. I'll try to host additional office hour before midterm 2 just to make up for it. All right, so that's for the next week. And next Friday is Veterans Day, so there will be no meeting. It's the university holiday. And that's all on the administrative end. Do we have any questions before we move on? Okay, and one very small thing. So some of you were emailing me about like, hey, we have this extra credit survey that I just missed the deadline because of my other midterm exams. So here's my policy. For this class, you have one chance to just ask for an extension for a Canvas assignment, like an extra credit item, like a survey or an extra credit assignment or anything on Canvas. Not on your worksheet or on your exam, but anything on those extra credit items on Canvas, you have one chance to just send me an email and say, give me an extension. I won't ask you anything, all right? And just one chance for this quarter. So just to give you a little bit flexibility over those extra credit items. Okay, any other questions? Nope, sounds good. So coming back to our today's lecture, I want to slow down a little bit because I feel like the last lecture was like equation after equation, and lots of people appear to be like very confused about what's going on over the derivation process. So I want to quickly pause here a little bit, just go over what is the relationship between all these equations we derived in our last lecture, so that you know what we're doing by doing these derivations. So everything in thermodynamics, again, the purpose here is we're trying to evaluate what are some of the abstract properties of a system, right? Entropy, internal energy, free energy. So these are the things we do not have a good means to measure experimentally. We have to somehow link these properties with experimentally measurable quantities. So in this process, we start from the 6 basic equations. Now, these two are the definition of your heat capacity at constant volume and constant pressure. This one is our first law of thermodynamics, and these 3 only hold true for closed system, PV work only, and reversible processes. The rest of the 3 are enthalpy, Holmes free energy, and Gibbs free energy. So please keep in mind what are the physical meaning of these 3 state functions, right? Enthalpy is your QP at constant P. It's a heat transfer at constant P. A, that's a work function. We went over the derivation and say, hey, A, that's the maximized amount of work your system can do on the surrounding, right? And G, that's the maximized amount of non-PV work your system can do on the surrounding. But these 3 are just by definition, they're always true, whatever system we're looking at. And then moving on, starting from these basic equations, we used calculus to derive what we call the Gibbs equation. So the process of Gibbs equation is basically we want to write the change or the infinitesimal change of these state functions as in this kind of form. It looks complicated, but let's just write that du term here. That's TdS minus PdV. And plus, if you forgot like why these are true, like definitely go back and review a little bit in why the delta U equals to TdS minus the du equals TdS minus PdV. And then what we do is basically using the definition of these terms, right? So your dH equals to the derivative of u plus pv. What we do is just write it out, right? So du equals to, well, this one we write it out as pdv plus vdp, and this ends up to be tds minus pdv plus pdv plus vdp. So some of the things cancel out. We end up getting tds plus vdp for our dh. All right, you can do the same, and I highly recommend you do that yourself so you know how that's being done instead of just remembering what this Gibbs equation looks like. You can do the same for dA and dG, like what we did here, to derive the full set of the Gibbs equation. And let's put it here. So that's a summary table for our Gibbs equation. Then from the Gibbs equation, we used it in two different ways for the Gibbs equation we just derived. The first one is from the total differential equation point of view. So what that means is that's the calculus we're using. Let's assume we have a new function z, which is dependent on x and y. Right? So if you write out the total differential of z, of function z, you can write it as a partial derivative of z over x at constant y times dx, plus partial derivative of z over y at constant x plus times dy. So that's just calculus. That's just whatever the nature of these differential equations. With that in hand, let's use our dH example again. So we know in our Gibbs equation, we have dH equals to TdS plus VdP. Or the other way to put it is our H is a function of S and P, right? It's a function of S and P here. So we can write this dH as a function of S and P, like what we did here. That's a partial derivative of H over S at constant P ds plus partial derivative of H over P at constant S dP. Right, so that's just writing out the total differential of your enthalpy, which is a function of S and P. Now with this equation and our Gibbs equation together, we have some information about these partial derivatives. Right, so the same thing in front of ds, we have T equals to partial derivative of H over S at constant P. And this term here, we have V equals to partial derivative of H over P at constant S. All right, so do the same kind of derivation for these four Gibbs equation. You get a table of these partial derivatives, linking it to some kind of macroscopic properties or like entropy state function. So that's the first use of our Gibbs equations. Sorry, I'm moving things a little bit around. Okay, so that's our first use. It's using the total differential equation. And then at the end of our last lecture, we went over the use of our Euler's reciprocity relations and with the Gibbs equation to derive the relationship between these partial derivatives. So what we have in the Euler's reciprocity relation is, again, if you have a function z as a function of x and y, right? Let's just write out the general formula for this equation. You have some kind of equation m times dx plus some kind of equation n times dy. So in calculus, the Euler's reciprocity relation tells you the partial derivative of m over y at constant x equals to the partial derivative of n over x at constant y. We went over a quick derivation for this relationship. I'm not going to test you on it, but it's going to be nice if you know how that's being derived. And then what we're using is now we have, instead of a random function z, we have our Maxwell relationships. And what we're doing is using our Maxwell relationships and the Euler's reciprocity relations to find equivalence between these partial derivatives. Again, let's use our delta H as an example. So we have the H equals to TdS plus VdP. Right, so if you look at here, T is our M, S is our X, V is our N, and P is our Y. That's the relationship here. So we can write out partial derivative of M over Y at constant X, which is S, equals to partial derivative of N over X at constant Y, which is P here. All right, and again, similarly, you can do the same kind of derivation for all four Gibbs equations. So here's the relationship. Everything is being derived from our fundamental basic equations. Like I know this class is open book, open note, but again, that's what I promised you at the beginning of the class, right? If you write down everything, sooner or later, you'll find yourself really lost in like what equation I should be using. I have so many different things to choose from. But just knowing how we're connecting it, like we have our basic equation, we use basic calculus and the definition of these state functions to derive a set of Gibbs equations. And then we use different calculation tools to find out relationship between partial derivatives and some of the properties, or partial derivatives with themselves. All right, so know how that's being done, and then know how to use it for your derivation problems. Any questions? That's a quick review on what we covered last lecture. All right. Then let's move on to the practical end. Like now we have all these relationships. We have all these like functions, all the relationships between the partial derivatives and everything. How are we actually using it? So the way to think about it is what we want to know is how does these seemingly abstract state function like internal energy, enthalpy, entropy, Gibbs free energy, right? So these are the things we care about, but we can't directly measure. So what exactly are their dependence on something you can measure, like macroscopic measurables, temperature, pressure, volume, or like coefficient that you can experimentally measure? How to build a link between these properties. Like if you search online, you have all those thermodynamic tables. Have you ever wondered like how people find out the standard enthalpy or standard entropy for a specific substance, right? So let's just work out 2 examples, and then you should try everything else yourself just to make sure you know how that's being done. Let's get started looking at the volume dependence of U. Okay. So if you don't have a copy of this Gibbs equation, just take a picture now, because we will be using the Gibbs equation along the way. Now, when we're talking about volume dependence of U at constant temperature, what we're talking about is how to derive from from our Gibbs equation, du equals to TdS minus PdV. Again, reading the question, we want to find the volume dependence of U, or what we want to find out is how does your internal energy change with respect to temperature. So naturally, the first step we do is taking the divide both sides of your equation by the change of temperature, or dT. So we have du over, sorry, we're talking about volume, it's dV. du over dV equals to temperature times ds over dV minus pressure times dV over dV. And we cancel that dV over dV term out. And then from here, we can assume this one is at constant temperature. And the reason we have to assume it is now we have a temperature in front of that ds over dv one. If we don't assume constant temperature, then this term becomes something we cannot solve for. So what we have is assume constant temperature. Now, after we assume it is constant temperature, we have two things we can do. First thing is now we can treat this temperature as a constant. We can move it out from that derivative. And second thing, these normal derivative now become a partial derivative at constant temperature. Right? We're only assuming the temperature is constant to get those partial derivatives, but temperature might be changing throughout the way. Just we want to get an expression for those partial derivatives. And then it becomes partial derivative of u over v at constant temperature equals temperature times partial derivative of s over v at constant temperature minus p. Okay? And then in here, we have this term. That's a partial derivative of your entropy over volume at constant t that we really don't know how exactly to solve it or to measure it experimentally. So that's a good point to hint. You should go back and check your Maxwell relations and see if you can find something to relate your change of entropy with volume at constant t. So let's check it out. So we're looking for something of partial derivative of entropy over volume at constant t, and here we go. Right, so that's one of our Maxwell relations. And we can copy that down. So from the Maxwell relations, we have partial derivative of ds over dv at constant t equals to partial derivative of p over t at constant v. And that's our Maxwell relations. So this term then becomes partial derivative of u over v at constant t equals to t times partial derivative of p over t at constant v minus p. Now we end up having a term that you feel is experimentally approachable. We're only talking about the relationship between pressure, temperature, and volume, which are things we can control. So this goes back to our lecture 2. We went over a careful derivation that all relationship of pressure, volume, temperature can be reduced to two different partial derivatives, which are alpha and chi. All right, so that derivation we went over back in lecture 2. But in here, let me just write down some of the things that will help you to solve for the relationships and check it yourself to prove why this term equals to alpha over chi. So a little bit of the hint. We have definition of alpha being 1 over v times partial derivative of v over t at constant p. Chi is defined as minus 1 over v times partial derivative of v over p at constant t. And when you have these partial derivatives moving around, we also have this rule of linking them together. So dp over t at constant v, dt over v at constant p, and dv over p at constant t. That product goes to -1. So using these relationships, you should be able to prove that your partial derivative of p over t at constant v equals to alpha over chi. If you don't know how to do that, definitely send us an email and let your TA and I know, and we'll post something for you. So try this one yourself. But nevertheless, the take-home message here is we end up deriving the partial derivative of your internal energy over volume at constant t to be temperature times alpha over chi minus p. And now everything in this expression are experimentally measurable. Right? Temperature, pressure, alpha, and chi, these are all the things we can measure experimentally. So that's the whole purpose of thermodynamics, and that's the whole purpose of well, I can't even finish all the equations on the board, but that's why we went over all this trouble of derivation. Any questions before we move on? Nope. Okay, every time this happens, I feel like either I'm like super clear or like people are super lost that they don't have anything to ask. But nevertheless, I hope it's the first, not the second. So for yourself, I hope you have the chance to derive the following representations of these partial derivatives. Some of them are pretty intuitive. For example, like this first one, right? When you have the partial derivative of h over t at constant p, that's pretty much our fundamental equation or the definition of your heat capacity. Like this one is also pretty counterintuitive. This comes from our relationship that you can derive from this end, so you can work that out as well. But there are some other ones that worth your trying, like this one and these relationships. It's definitely worth your trying to see how that's being done. All right, so that's the end of our lecture 9, our slides lecture 9, but not today's lecture. And then let's move on to our next chapter. Well, not next chapter, the next section of the same chapter. So I think my goal here today is to finish talking about 4.5. We'll save the 4.6 and 4.8, where we move from the equilibrium world. Now we're always talking about things in equilibrium with each other. And from our next lecture, we'll move away from 100% equilibrium world and think about how exactly are chemical reactions taking place. So this part will feel like an application. So what we're doing here is using whatever we just learned, all the equations, to solve for actual expression in how can we calculate these changes in state functions, like apply what we learned before to specific questions. So let's get started. Let's start from entropy, which is a function of temperature and pressure. So in this case, again, the first thing to think about is what is your initial state and final state. Let's think about the process where both your temperature and pressure are changing for that process. So your initial pressure and final pressure are different. Initial temperature and final temperature are different. And then in here, I'm just going to write down some of the things you can derive using the Gibbs equation. So that is ds equals to the partial derivative of s over p at constant t dp plus partial derivative of s over t at constant p dt. Right, so this one is just writing out the total differential for your delta S. And in here, these are the things that you can derive when we say the dependence of entropy on pressure and temperature. So those are the things you can derive, like the example we just did. Right, just instead of the internal energy's dependence on volume, now we're talking about the entropy's dependence on pressure and temperature. So these are the things you can try to derive. And these partial derivatives, well, the first one, the pressure dependence of entropy equals to negative alpha times V. The temperature dependence of entropy equals to Cp over T. And let me just go back to make sure you have it. And that's what we are using here. All right, so that's where we are using. And if you don't know how we get to there, just try derive it yourself. It's not hard, I promise you that. Okay, so go back to this example. Don't freeze. Go back to this example. Now what we have is ds equals to negative alpha v dP plus Cp over T dt. Or if we want the delta S, we need to take the integral on both ends of your equation. So taking integral, we end up having delta S equals to negative 1, 2, or P1, P2 for alpha V dP plus T1, T2 Cp T dt. All right, so we have two parts of this integral. The first part is depending on the pressure change. The second part depends on the temperature change. We don't know how this reaction takes place, but what we do know is that your entropy is a state function. So we don't care how it takes place. We can make our life much easier by assuming, say, the first step. So let me just write it down. So S is a state function. So we can build a path that's making our life easier. So what we have is start from P1, T1. We can assume the first step is a constant pressure process or isobaric process. And we can calculate this delta SA from P1, T1 to P1, T2. Right, so for your delta SA, your temperature change is the only thing that contributes to your delta SA. The pressure is remain the same. So your delta SA equals to T1, T2, Cp over T dt. All right, and then we can define a second process, which is a constant temperature. And that's, we call it delta SB. And that goes to give us like the final result is P2, T2. And my delta SB, the temperature remain the same, so only the first term contributes to the overall process. We have delta SB equals to P1, P2, alpha V dP. All right, and what about the total entropy? That's just the delta SA plus delta SB, which gives you the final result. Okay, and let's do an example together, just using whatever we just worked out in a real example. So if we read the question together, it says calculate delta S. Let me just turn off this light here. Or is it okay if I leave the lights on? Okay. So let's read the question together, right? Calculate delta S when 2 mole of water goes from 27 degrees Celsius at 1 atm to 37 degrees Celsius and 40 atm. And it gives you some of the constants in example 4.2, and I just rewrite these constants here that you will come to use. It also tells you you can neglect the pressure and temperature dependence of your heat capacity and your alpha and also your volume. So we're assuming these things remain unchanged. So for our exam, I'll try my best to keep the same level of information to you. Like if we're assuming something is not changed, we'll specify it's remain constant. If we tell you something is an ideal gas, we'll specify it in the problem that is an ideal gas. If we didn't say anything, do not make that assumption. Like especially do not make that assumption for ideal gases. I know we spend lots of time talking about ideal gases, but unless we specify it being an ideal gas, don't make that assumption. All right. So let's get started by just writing out what we know. We have the initial state, right? It asks for delta S, so naturally we want to know what's our initial state, what's our final state, how do we approach it? So the initial state, we have P1 equals to 1 atm, T1 equals to 300K. And our final state, we have P1 equals to, P2 equals to 40 atm, and temperature equals to 310 Kelvin. So if you don't have a copy of this example question, just take a picture because we'll be moving on. And then, like what we just did, let's build a hypothetical path where we keep the pressure constant for the first step and then keep the temperature constant for the second step. So let's assume we have an intermediate state. Where your pressure has been kept constant, equals to P1 equals to 1 atm, and your temperature equals to T2, which is 310 Kelvin. All right, so in this process, the first step is constant P. The second step is a constant temperature. And let's set up our calculation together. What do we know for a constant pressure process? So going back here, for a constant pressure process, this first term goes to 0. We only care about the second term. So what we have is this delta S equals to the integral of Cp over T dt. So we can write that out to be delta SA equals to T1, T2, Cp over T dt. Now, in this example, we're assuming Cp being a constant, and we're giving you that number here, so we can take Cp out. Well, this one only gives you Cpm, which is the molar heat capacity. So translate that molar heat capacity to the actual heat capacity. We can get N Cpm T1, T2, 1 over T dt. And that gives you N Cpm ln T2 and T1. So here we're not plugging numbers yet. I'm just trying to make sure I have all the information to solve for this integral. Now, do I have all the information? Number of moles, yes, we know it's 2 more. Cpm, we have the number here. The initial temperature, T1, is 300K. Final temperature, T2, is 310K. So then the plug-in number should be pretty straightforward, but I just like to set up the integral here. And doing the same for the second step. So it's a constant temperature process. So delta SB, now your temperature term goes to 0, and we only care about this pressure term. So what we have is delta SB equals to negative P1 to P2 alpha V dP. Now in this case, we are assuming that alpha and V are independent from pressure and temperature, so both of them are constant. And we have those numbers here, right? Vm equals to 18.1, and your alpha equals to 3.4 times 10 to the negative 4. So those are constant as given. And you can rewrite it as alpha N times Vm. That's just taking consideration of volume and molar volume, and P2 minus P1. All right. So at the end, what we have is delta S equals to delta SA plus delta SB. We end up having this term, the N times heat capacity times ln T2 over T1, and minus, well, the SB term, plus the SB term, but it happens to have a minus in front of it, the alpha N Vm P2 minus P1. Now, do we have all the numbers in here? Now, this one is no, the number of mole is no, the heat capacity is known, the temperature, initial and final temperature is known, alpha is known, N is known, Vm is known, P2 and P1 are known. We're just plugging all those numbers to get a final result. So again, like if this is one of your exam questions, you give me this, you already get like 70% of your grade. I mean, if your calculation is somehow wrong, the maximum amount of grade you're gonna lose is only 30%. So spend more time thinking about how to set up the calculation correctly rather than plugging numbers and try to get those numbers correctly, right? Any questions for this example? Nope. Okay, sounds good. Let's move on. And then we have our other state functions, for example, delta H and delta P. Now I put delta H and delta P together because they are only different by a PV coefficient here. And both P and V are something experimentally you can measure, or you have a mean to take consideration of the PV coefficient. So I put them together here. So when we have the Gibbs equation for dH, we write it out as dH as a function of T and P. That equals to partial derivative of H over T at constant P dt plus partial derivative of H over P at constant T dP. And then we can go back and check what these partial derivatives are. Back to our note. Maybe I shouldn't jump back and forth because it keeps freeze on me. And that's what we're having here. No, not this one. All right, so what we can write is this partial derivative of dH over dt at constant P equals to P, and the right one equals to negative TV alpha plus V. And again, if you don't know how these are being done, just derive it yourself. And then we can rewrite our expression here. So dH as a function of Tp equals to Cp dt minus TV alpha plus V dP. Or take the integral on both ends. We got delta H equals to T1, T2, Cp dt minus P1, P2, TV alpha plus V dP. Your delta U just equals to delta H minus delta PV. And again, like PV is something experimentally we can take care of. So we don't have to necessarily do that derivation again for du. You can actually try it out and see the delta U you get using this approach and also the delta U you get using this partial derivative approach. They should give you the same answer. So try it out and like check it out. All right, yes? Oh yeah, you're right. Let me just do this. Okay? Yeah, and then just do the derivation of du using the same kind of logic or the different logic using this kind of logic, or use delta H minus delta PV and try it again. Okay. The next one we want to move on is Gibbs free energy. So when we look at Gibbs free energy, we have G is defined as H minus Ts. So both of the terms we just derived. So if we're considering an isothermal process, we have delta G equals to delta H minus T delta S. And these are the things we just discussed, right? So delta H equals to this term, and delta H equals to this term, and delta S we just derived before. So you have a way to talk about what is your delta G at constant temperature. Okay. And also from the pressure dependence of G, we have an interesting expression of partial derivative of G over P at constant T gives you volume. And then what else we know is at constant T, your dG over dP does become a normal coefficient, normal derivative at constant temperature, so that partial derivative becomes dG over dP equals to V. Or you have dG equals to VdP. And you can also calculate your delta G using this relationship. And again, like we have two different ways to solve for delta G, so try it yourself to make sure they give you the same answer. And then let's spend just a little bit more time thinking about delta G and the nature of delta G in chemistry. So if we consider a reversible process at constant temperature and pressure with only PV work, so that's something, if your reaction is slow, that's something that's always we are able to achieve. So what we have is at constant pressure, let me use a different color. This you can instantaneously write delta H equals to QP at constant pressure. What else we can write? We can write ds equals to dq over T because this is a reversible process. All right, or delta S equals to Q over T. And then, and that's constant Tp as well, we have delta G equals to delta H minus T delta S. So your delta H equals to Q. Your T delta S also equals to Q. So your delta G equals to 0 for any reversible process at constant temperature and pressure with PV work only. So that's why delta G equals to 0 becomes our criteria to evaluate whether or not your chemical reaction is at equilibrium. Okay. There are a lot more examples we can do, but let's just do one more example that's a little bit heavy on derivation, and I think lots of people are confused by this type of problem. So the example I picked here is 4.32. So it tells you a certain gas obeys this, well, some kind of equation of state, where PVM equals RT times 1 plus BP plus CP squared. It tells you B and C are constant. Ask you to find an expression for delta H, molar delta H or delta HM, and delta SM for a change of state of this gas from P1T1 to P2T2. It tells you can neglect the temperature and pressure dependence of CPM. So the way to think about this problem is you should leave that equation of state aside until we find out an expression for delta S and delta H. And then we use equation of state to find an expression for your alpha or V or T, and then write out that final expression. So let's see how that's being done. So the way to think about it is let's write out what we know, right? So delta H equals to Cp dt from T1 to T2 plus V minus TV alpha dp from P1 to P2. And also we know delta S equals to 1 to 2 Cp over T dt minus 1 to 2 alpha V dp. So write out these two expressions first, because eventually we will use these expressions to write out the final expression of delta H and delta S. And then, since this process involves alpha in both of these expressions, let's write out the definition of alpha being 1 over V, partial derivative of V over T at constant P. All right, so what do we need in this process? What do we need to solve this integral? So we want to use our equation of state to solve for an expression of alpha. And then we plug in that alpha into this expression of delta H and delta S to find that final expression. So we use the equation of state at a later stage. The equation of state has nothing to do with what delta H and delta S are being defined to. Equation of state only tells you how to express your alpha without that partial derivative term. And that's why we spend lots of time like writing out or trying those derivations, giving a random equation of state, write out an expression for alpha or for chi. Now in this problem, we can work on that derivation together. So again, if you want to take a picture, please do that right now. So we have the equation of state, which tells me V equals to nRT times 1 plus BP plus Cp squared over P. And here our alpha thus becomes 1 over V. You do that partial derivative. Now this one is pretty straightforward. You only have one dependent of T here. You have 1 over V times wait, let me just not skipping any steps. So 1 over V times partial derivative of V over T at constant P. We can rewrite that V, 1 over V term here to be P over nRT times 1 plus BP plus Cp squared. And on the right-hand side, this T just leaves in that derivative. You have nR times 1 plus BP plus Cp squared over P. All right, so what we end up having is just 1 over T for this expression of alpha. And then what we're doing is just plugging that alpha back into our original expression. So using our delta H as an example. In this case, let's look at the first term. This one just stays the same, T1, T2, Cp dt. And on the right-hand side, this one is sort of curious. So we have V minus T times V times alpha. So it's T, V, 1 over T. Right, so alpha equals to 1 over T, that's how we derive. So T and T cancel out, and V minus V goes to 0. So this last term just goes to 0. What we end up having, because we know Cp is not dependent on temperature, so we can take it out. So we can delta H, molar delta H equals to the molar heat capacity times delta T. And delta T is just T2 minus T1. All right, so the logic here for this kind of question, you can do that for delta S as well. I'm not going to spend time doing it. You can try it yourself. So the logic of this kind of problem is write out that expression for your state function first, and then think about how to use the equation of state to solve for those coefficients. like alpha and chi, or even the Joule coefficient or Joule-Thomson coefficient. All right? I think we're running out of time. I guess in our next lecture, we'll start talking about chemical potentials, and we're moving out from non-equilibrium systems. All right, see you next time.